Okay, let's start again from your 10th slide, in which we have the model that we are talking about, which is first order um, extravascular model. We have first order, we have first order absorption rate constant, elimination rate constant, we have XGI, and we have XP. XGI, again, it's absorbable amount or available to be absorbed at the site of absorption. First order rate constant, amount that is remained to or in the body, and the elimination rate constant. Okay, first order. Again, we are still talking about one compartment model, single dose, and this, as we are saying, extra vascular, but as we are saying, GI, so it's oral single dose and first order kinetic. Okay, so those are the definitions of all the symptoms. If I took this part only, and I will talk about the change and the amount at the absorption site per unit of time. Okay, so it's XGI that is disappearing. I'm not talking about the whole model, I'm just talking about as you are having XGI and it's decreasing. If you remember, when we were talking before, again, this is a side note, when we were talking before about XP, X node, K, and IV bolus, right? It was decreasing of the amount in the body. And when we were having the differential equation, we had, right? And it was equal minus K multiplied to XP at certain time. Okay, this is the rate of change and the amount per unit of time when we called it elimination. Oops, we lost it. So another one, elimination rate, right? It's elimination rate. It was equal minus because it's decreasing K, which is first order elimination rate constant, XP. This is a differential equation, and when we have it as after the integration, we had it as XP at certain time equals X naught exponential minus K multiplied to time. You remember this, right? This was, again, something that we took earlier for the amount in the body that is decreasing when we were talking about X and the body and IV bolus. Let's go back here. If, again, I will draw it here. I will draw it as compartment, but you can consider it as not. XGI, the amount that you have available to be absorbed, and Ka. So we have first order absorption rate constant and amount, and I want to talk about amount of disappearance or decrease or change in the GI at certain time. Similar to whatever you know here, but we are just changing what we are talking about, right? It's just the same concept, but we are changing what we are talking about. It's symbols or places or locations, but it's the same. So this will be equal decrease because it's decreasing Ka, right? Because absorption rate constant multiplied to amount in the GI at certain time. Similar to whatever you know here, but it's in GI. Absorption rate constant and GI at certain time, right? When this differential equation is integrated, we will have XGI at certain time that is equal to XGI naught multiplied to the exponent minus Ka multiplied to the time, similar to whatever you have here. Again, you can review the integration rules that we talk about it before, but you can just know it by concept. If you know this, this will be the same. Okay, this, it's the initial amount that we have here, the initial amount that we have here. Okay, and the initial amount that you have here, it won't be equal x naught, right? Here it was equal to x naught because the whole dose entering the body. We don't have it completely here. It will be fraction of the dose, okay, multiplied to E Ka multiplied to the time. This is equal xgi at certain time. Okay, this xgi, which is here initial, will be equal to the x naught under one condition, which is when your F is equal to 1, which means when the drug is 100% bioavailable or all the dose reaching the amount, initial amount at the site of absorption. So this is my equation, either this or either this. Okay, and by this I'm finishing whatever that you have in your slide 11. Can I draw this? So this, I think, was my third slide. I want to play around with this to know if I can determine certain kind of stuff kinetic wise or parameters that I have. So xgi at certain time equals xgi naught E minus Ka multiplied to the time, in which this equal F multiplied to x naught, right? I just said that. Again, it's a mono-exponential equation. Can I draw it or determine it according to whatever you know earlier? It's similar to whatever you have before in this equation. Again, side note, x b certain time equal x naught minus k bit time. We had this earlier and we were able to draw it in our four graphs or diagrams. If I have xgi versus time, xgi versus time, rectilinear, semilog, rectilinear, rectilinear, log, xgi, len, xgi. I will have, can we draw this? Yes, for sure we can. This will be mono-exponential graph or profile with this equal xgi naught, right? I will have this because it's on a semilog with this xgi naught, which again it's equal F multiplied to x naught, and I will have this here, I will have this here linear, but this will be log xgi naught and this will be len xgi naught. Similar to whatever you know earlier related to whatever we draw here in the amount or concentration in IV bolus. So similar kind of thing. So I can determine according to those graph xgi, which if I know it by knowing the dose, I can know the fraction of the drug or the bioavailability of the drug. And according to this equation, I can use this to determine what Ka, which is the absorption rate constant, right, from the slope or from the slope of the linear regression of the profile either here or there, right? And if you know Ka, you will be able to determine the absorption half-life, which is equal 0.693 over Ka. So I was able to determine xgi, F, which is the fraction of the bioavailable drug, Ka, and absorption half-life, right? Mathematically we can do that, kinetically we can do that, but we have a problem, which is to do this before. In here, again, let's do a side note here. We were either drawing amount in the body versus time to have this, which was measured at concentration in the blood or plasma or whatsoever, and we have this, right? So to have it, you will have a measurement of concentration of the drug versus time. So you take these samples of concentration in the blood at different time points, which was experimentally feasible. And here, to have this, you need to do a measurement of the drug at different time points in GI. Let's go back. GI is the amount, right, available to be absorbed in the lumen of the GI. Is it feasible to take different samples of the drug from the GI at different time points to be able to do this profile? No, it's not. So experimentally we can't do that, but just hold on this principle because we will use it after all in another principle. And this is your fourth note. Okay? By this, we are ending your 13th slide, and for this, for sure, we will do a measurement either in the compartment itself in the blood or either in the urine or both of them. So we will talk first about this, then we will talk about the urine measurement. So we will have either measurement in the blood or measurement in the urine. Okay, and this will be the end of the video recording number 2. Assalamu alaikum.